Imagine winning the Nobel Prize. You are standing on a stage in Sweden, receiving the absolute highest pinnacle of scientific achievement, while the entire world just applauds your genius.
Right, the ultimate dream.
Exactly. But now imagine finding out later that the brilliant discovery you won that prize for was completely 100% wrong. And worse, your mistake inadvertently handed humanity the instructions for the atomic bomb. Okay, let's unpack this. Welcome to this deep dive.
Thanks, I'm really excited for this one.
So today, our mission is to explore the extraordinary life and mind of Enrico Fermi. We're looking at a huge stack of biographies and historical records to understand how the so-called architect of the nuclear age possessed this totally unique way of viewing the universe. It was this wild blend of genius-level mathematics and, well, back-of-the-envelope simplicity that forever altered the course of human history.
Yeah, and that paradox of the Nobel mistake, that is the perfect entry point. We tend to view scientific progress as this flawless straight line drawn by infallible geniuses. But Fermi's story just completely shatters that illusion.
It really does.
To understand how a mind capable of such profound leaps could make an error of that magnitude, and how that error ultimately sparked the first nuclear reactor, we really need to look at how he built his foundational understanding of the world.
So let's go back to Rome, Italy, in the early 1900s. Fermi is this young kid, and he's wandering through a local market, the Campo dei Fiori, and he spots a physics book.
Right.
Now, this isn't some, beginner's guide with nice illustrations. This is a massive 900-page text covering complex mathematics, classical mechanics, astronomy. It was published in 1840. And here is the truly absurd part. It is written entirely in Latin.
And he bought it with his allowance and just devoured it. We were talking about a teenager who fundamentally taught himself the architecture of the physical world.
Just for...
Exactly. He and a friend started building their own gyroscopes and measuring the acceleration of Earth's gravity just for fun. By the time he applied to the prestigious Scuola Normale Superiore in Pisa, his entrance exam essay was staggering. At 17, he used complex Fourier analysis to solve a partial differential equation for a vibrating rod.
Okay, wait. For those of us listening who don't speak advanced calculus, what does that actually mean? Because it sounds like he wasn't just doing basic algebra.
Oh, far from it. Fourier analysis is essentially a way of taking a really complex waveform and breaking it down into its simplest components. So think of it like taking a complex musical chord and isolating every individual note.
Oh.
Yeah, so Fermi was mathematically modeling exactly how a physical, solid object moves and vibrates in real time. He was translating the messy physical world into pure, elegant math.
Which I guess explains what happened next. Yeah. So he gets into the university, and his physics professor, Luigi Puccianti, calls this teenager into his office. And Puccianti basically throws his hands up and says, I have absolutely nothing to teach you. Actually, could you teach me about quantum physics?
Yeah, that anecdote perfectly illustrates a massive shift happening in science at the time. Physics was deeply divided into two camps. You had theoretical physicists who wrestled with abstract mathematics on chalkboards, trying to deduce the laws of nature.
Right.
And then you had experimental physicists who got their hands dirty in the lab, building equipment and just smashing things together, and you rarely crossed over.
Usually those are completely different species. It's like an architect who designs a massive skyscraper on paper versus the bricklayer who actually gets out there and builds the walls.
Yeah.
But Fermi was somehow the master architect who was also out there perfectly laying the bricks.
He really was. His colleague, Emilio Segre, later referred to him as the last universal physicist. His team in Rome revered him so much they actually nicknamed him the Pope.
Because his scientific pronouncements were considered totally infallible. Like, if Fermi said it was true, nobody questioned it.
Right, which becomes deeply ironic given where we are heading. But first, the Pope waded into a massive crisis in the physics community. In the early 1930s, scientists were entirely puzzled by something called beta decay.
Right, this is where atoms emit electrons.
Exactly. An atom would naturally emit an electron, but when researchers carefully measured the energy before and after this process, some energy was literally missing.
Which violates the law of conservation of energy. You can't just lose energy into the void. It has to go somewhere.
Right. So Wolfgang Pauli floated this radical idea. Maybe there's an invisible, almost entirely undetectable ghost particle carrying that missing energy away. Fermi grabbed onto this concept, built out the rigorous mathematical framework for how it would function, and named this theoretical particle the neutrino.
Which is Italian for the little neutral one, right?
Exactly. So he submitted his groundbreaking paper on this to the highly prestigious British journal Nature.
Oh, I was reading about this rejection letter, and I was genuinely stunned. The editors of Nature essentially laughed him out of the room.
They really did.
They told Fermi his idea was, quote, too remote from physical reality to be of interest to readers.
It is easily one of the worst editorial decisions in scientific history, especially considering the neutrino is a foundational pillar of the standard model of physics today. But, that sting of rejection pushed Fermi away from pure theory.
He wanted to win.
Yeah, he decided he wanted to see tangible, undeniable results, so he pivoted back to experimental physics in his Rome laboratory. And he started playing with a newly discovered piece of the atomic puzzle, the neutron.
Okay, so this is where we get the famous tabletop experiment.
Mhm.
Fermi and his brilliant group of young colleagues, they called themselves the Via Panisperna Boys, they were bombarding all sorts of different chemical elements with neutrons to induce radioactivity. But their results were completely erratic. Nothing made sense.
Right, they noticed a baffling anomaly. If they conducted the exact same neutron bombardment experiment on a wooden table, the radioactivity increased significantly compared to when they did it on a marble table.
That sounds like actual magic, like wood versus marble altering a subatomic experiment. But Fermi's brain doesn't just accept it as a weird quirk. He stops and asks, well, what is the chemical difference?
And he realizes wood has a high concentration of hydrogen, marble doesn't.
Right, so he has this flash of insight. He remembers that paraffin wax is also densely packed with hydrogen. He grabs a block of paraffin wax, places it directly in front of the neutron source, and tries the experiment again. The induced radioactivity doesn't just bump up, it spikes 100 times higher.
Yeah, and here's the underlying mechanism driving that spike. Neutrons, as the name implies, have a neutral electrical charge. So they aren't repelled by the positive charge of an atom's nucleus, they can wander right in.
Okay, makes sense.
However, if a neutron is fired out of a source moving too fast, it just zips right past or punches clean through the nucleus without interacting. But when that fast neutron hits the hydrogen atoms in the paraffin wax or the wooden table, it behaves like a billiard ball, striking another billiard ball of the exact same weight.
It bounces.
Exactly. It bounces, loses a massive amount of kinetic energy, and radically slows down.
I love thinking about this like a sports analogy. It's like trying to catch a baseball. If someone fires a baseball at you out of an air cannon, it's going to bounce right off your hands or, break your fingers. You physically can't catch it.
Definitely not.
But if they lob that same baseball to you in a gentle, slow arc, you can easily snatch it right out of the air. So the hydrogen in the wax essentially lobbed the neutron so the atomic nucleus could effortlessly catch it.
That's a perfect way to look at it. Those slow neutrons were easily captured by the nucleus, instantly creating a heavier, unstable radioactive isotope. Fermi realized he had found a skeleton key for the atom.
So he just starts testing everything.
He methodically worked his way through the entire periodic table, bombarding everything he could find with slow neutrons. Eventually, he reached the very end of the known table, which was uranium, the heaviest natural element.
Right.
He fired his slow neutrons at uranium, detected new, highly radioactive substances, and concluded that his nucleus had swallowed the neutron and grown heavier. He fully believed he had created brand new, artificially heavy elements, which he proudly named oscenium and hesperium.
And the scientific community completely lost their minds over this. I mean, he had seemingly expanded the fundamental building blocks of the universe. In 1938, at 77 years old, Fermi is awarded the Nobel Prize in Physics for this specific discovery.
A massive achievement.
So he travels to Stockholm, receives the medal, delivers his acceptance speech, and then the floor just totally falls out from under him.
Yeah. While Fermi was in the spotlight, a team of scientists in Germany, Otto Hahn, Fritz Strassmann, Lise Meitner, and Otto Frisch, were quietly scrutinizing those exact same uranium experiments. And through meticulous chemical analysis, they realized Fermi hadn't created new, heavier elements at all.
He would actually split the uranium atom entirely in half. It was nuclear fission. The entire time he thought he was building the atom up, he was actually tearing it apart.
Exactly. The new substances Fermi detected were not oscenium and hesperium. They were much lighter elements, primarily barium, which were literally the fragmented remains of the smashed uranium atom.
Okay, I have to stop you there because calling him infallible, calling him the Pope, feels crazy when you look at the historical record here. I read in the source material that a female chemist named Ida Noddack actually warned him years earlier.
She did, yeah.
She explicitly suggested that his neutron bombardment was breaking the nucleus into large fragments. And the Pope of Physics just dismissed her. How does a genius just ignore the biggest scientific discovery of the century when it's literally handed to him?
Well, that oversight really reveals how even the most brilliant minds are constrained by the established paradigms of their era. Based on the physics of the time, Fermi miscalculated the binding energy of the nucleus.
The glue holding the atom together.
Exactly, the strong nuclear force. He assumed firing a tiny neutron at a massive uranium atom was like shooting a BB gun at a bowling ball. He figured the BB would just stick, making the ball slightly heavier.
Right.
He couldn't mathematically conceive that a slow-moving BB could hit a structural weak spot and shatter the entire bowling ball. He was so incredibly confident in his theoretical math about that binding energy that he didn't seriously entertain Noddack's alternative.
Wow. So he finds out he was completely wrong. He is deeply embarrassed. He literally has to write a footnote into the published version of his Nobel acceptance speech admitting his monumental mistake.
Yeah, that must have stung.
But while this intense scientific drama is unfolding, an incredibly dark human drama is running parallel to it.
Yes. By 1938, Benito Mussolini has aligned fascist Italy tightly with Nazi Germany, and he introduces these devastating Italian racial laws.
Which is terrifying because Fermi's wife Laura is Jewish.
Right. Fermi had joined the fascist party years earlier merely for career survival and funding, but these new laws presented a direct mortal threat to his family. So they used the Nobel ceremony as an escape route.
Such a risky move.
It was. Instead of returning to Rome after Stockholm, the Fermi family boarded an ocean liner and fled to New York City as refugees.
And just think about the timing here, because this is where history turns on a dime. Fermi arrives in America in January 1939. He is a refugee escaping fascism.
Right.
But he is a refugee who has just been handed the verified, terrifying secret of nuclear fission by his colleagues.
Right.
Furthermore, he understands the mechanics of slow neutrons better than any human being alive. He is perfectly positioned to build the first atomic fire.
And he knew exactly what was at stake. Fission doesn't just release a massive amount of binding energy, it also releases additional neutrons. Fermi realized that if you could slow those newly freed neutrons down, they would go on to split other uranium atoms, which would release more neutrons and so on.
It would create a self-sustaining chain reaction.
Precisely. But they hit a massive engineering wall. They needed a moderator to slow the neutrons down, just like the paraffin wax from Rome. Water works, but water also absorbs too many neutrons, killing the reaction.
So what did they do?
Fermi suggests using pure graphite instead. And this theoretical debate leads to one of the most surreal moments in scientific history, the building of Chicago Pile 1.
The U.S. government had initiated the Manhattan Project. But before committing massive industrial resources to build a bomb, they needed proof that a controlled nuclear chain reaction was even possible in reality.
Right, they needed a proof of concept.
So Fermi's team at the University of Chicago began assembling a literal pile of uranium oxide blocks and thousands of graphite bricks. And they built it inside a squash court, under the viewing stands of Stagg Field, in the absolute middle of Chicago.
I know, it's...
Wait, weren't they utterly terrified of causing a catastrophic nuclear meltdown right there in a densely populated city?
Looking back, it seems like utter madness. Originally, the reactor was supposed to be built in an isolated forest preserve about 20 miles outside the city, but a labor strike halted construction.
Oh, wow.
So Fermi stepped in with his trademark supreme confidence. Relying on his meticulous calculations, he convinced the project leaders that he knew exactly how the pile would behave. He promised he could control the reaction with primitive cadmium control rods, and, well, they trusted the Pope.
So December 2nd, 1942, they slowly pull the control rods out of the pile. The clicking of the Geiger counters turns into a steady roar. It works. The very first human-created self-sustaining nuclear chain reaction.
An incredible moment.
Arthur Compton, one of the project leaders, runs to a phone and makes a famous coded call to Washington. He says the Italian navigator has just landed in the New World.
And that New World changed the entire trajectory of the war. But, you know, a squash court reactor produces only a tiny fraction of a watt of power.
Barely enough to power a light bulb.
Exactly. To build a functional atomic bomb, they needed plutonium. And to synthesize plutonium, they needed massive industrial-scale reactors. That requirement pushed the project out to the Hanford site in Washington state, where they constructed the massive B reactor.
Right. DuPont engineers built this enormous water-cooled reactor based on Fermi's scaled-up designs. In 1944, Fermi himself inserts the first uranium slug, The reactor goes critical, the power climbs steadily, and then out of nowhere it just starts dying. The power levels plummet, and the reactor completely shuts itself down.
The panic among the military and the engineers was absolute. Was there a massive leak? Had the facility been sabotaged by spies? I mean, this multi-million-dollar reactor sat completely dead.
Unbelievable.
But then, inexplicably, a few hours later, it started up again on its own, reached full power, and then died once more.
It's literally a ghost in the machine. With the fate of the global war hanging in the balance, Fermi starts frantically consulting with another brilliant physicist, Chen Xiongwu.
Yes. Chen Xiongwu had recently written a crucial, unpublished paper on a specific radioactive isotope called xenon-135. Fermi and his colleague John Wheeler analyzed her research and realized the nightmare scenario.
What was it?
Xenon-135 was a byproduct created during the fission process happening inside the reactor. And this specific isotope was a massive neutron sponge. It had a voracious appetite for absorbing neutrons.
Oh, so the reactor was literally choking itself to death. The fission created xenon, the xenon ate all the neutrons, which instantly starved the chain reaction. Once the reactor shut down, the xenon would slowly radioactively decay away, the neutrons would bounce back, and the reactor would wake up again.
Exactly. It was a seemingly insurmountable physics problem. But a combination of sheer engineering luck and Fermi's brutal logic saved the Manhattan Project.
How so?
When DuPont originally built the reactor, the theoretical scientists told them they only needed 1,500 tubes of uranium to achieve criticality. But the DuPont engineers, preferring to over-engineer everything just in case, drilled 504 extra tubes into the corners of the reactor block.
I read the scientists actually fought them on this. They thought adding those extra tubes was a stupid waste of time and money that was just delaying the project.
Oh, they absolutely hated the design. But Fermi realized that because of this xenon poisoning effect, those original 1,500 tubes would never produce enough neutrons to overcome the loss.
They needed to overpower it.
Right, they needed to brute force their way past the xenon sponge. By loading up all 2,004 tubes, including those wasteful extra ones, they could push the reactor's power level high enough to literally burn through the xenon poisoning faster than it could shut them down.
That is wild. And that brute force success at Hanford meant they finally had the plutonium? And that shifted the entire project from theoretical physics and squash courts to a terrifying practical reality in the New Mexico desert, Los Alamos.
Yeah, Fermi was brought out to the secret Los Alamos laboratory to serve as an associate director, heading up F Division, a specialized troubleshooting unit literally named after him. And he was standing in the bunker for the Trinity test on July 16th, 1945, watching the very first detonation of a nuclear weapon.
And okay, here's where it gets really interesting. This detail stands out to me so much because it perfectly encapsulates who he was. You have the most advanced, complex, terrifying piece of technology ever created by humanity exploding in the distance. And what does Fermi do? He executes what became legendary among scientists as the Fermi method.
Yes, the Fermi method is the art of getting highly accurate approximations through simple deductive logic. He absolutely despised overly complicated theoretical models if a back-of-the-envelope calculation could get you within striking distance of the truth.
It's like accurately guessing how many piano tuners live in Chicago just by estimating the population, the number of households with a piano, and how often a piano goes out of tune. It's pure deductive logic cutting through all the noise.
Exactly.
So during the nuclear blast, as the shock wave is violently rushing toward their observation bunker, Fermi stands up and drops small strips of paper into the air.
And as the blast wave hits the bunker, it blows those falling paper strips a specific distance backward. Fermi calmly paces off the exact distance the paper traveled, pulls out his pocket slide rule, crunches the kinetic energy displacement, and declares the bomb's yield to be roughly 10 kilotons of TNT.
And weeks later, after teams of scientists analyzed mountains of incredibly complex sensor data, they determined the actual yield was about 18.6 kilotons. He was in the right order of magnitude, off by less than a factor of 2, just by dropping scraps of paper.
That ability to strip a chaotic event down to its fundamental variables was his superpower. But, to fully understand Fermi, we have to look at the man after the dust settled, because the atomic bomb changed his worldview deeply.
Right, he wasn't just a cold calculating machine. A few years later, when the United States government started aggressively developing the hydrogen bomb, which is a thermonuclear weapon thousands of times more powerful than the atomic bomb they dropped on Japan, Fermi actually pushed back. He and his close friend, physicist Isidore Rabi, strongly opposed it.
They co-authored a fiercely worded minority report arguing against the H-bomb's development. They objected on technical grounds, but more importantly on moral grounds, stating it basically became a weapon of genocide rather than a military tool.
Wow.
Fermi also publicly testified on behalf of J. Robert Oppenheimer during his infamous security clearance hearings, defending his colleague against the aggressive political witch hunts of the era. He clearly saw the existential danger of an unchecked arms race.
He was thinking about survival, not just for nations, but on a cosmic scale. Have you ever looked up at the stars on a clear night and wondered, where is everybody?
The Fermi paradox.
Yes. That question is famously known as the Fermi paradox. He literally sat down at lunch with colleagues one day, quickly calculated the vast number of stars in the galaxy and the high probability of habitable planets, and deduced that the universe should be absolutely teeming with advanced alien life. And yet, we hear nothing but total silence.
That chilling contradiction still haunts astronomers and philosophers today. Tragically, Fermi didn't live long enough to explore it deeply. In 1954, he passed away from inoperable stomach cancer at the age of just 53.
That's so young.
It is. He was acutely aware that working hands-on with unshielded radiation for decades carried massive physical risks. Several of his closest researchers had also died prematurely. But he firmly believed the scientific advancement of humanity outweighed the danger to his own life.
So bringing all of this together, what does this actually mean for you, the listener? When you zoom out and look at the arc of this man's life, from reading a Latin physics book in Rome, to inadvertently splitting the atom, to dropping paper strips in the blinding light of a nuclear blast.
Fermi's life demonstrates that the most overwhelming, incredibly complex problems in our universe, whether it's the invisible inner mechanics of a decaying atom or the terrifying release of cosmic energy, they can be understood. They can be solved by stripping away the intimidation factor and breaking them down into simple, logical pieces. He basically made the terrifying universe approachable.
He really showed us how to read the rule book of nature, but he also left us with a massive, lingering responsibility. Toward the very end of his life, Fermi stated that he fervently hoped mankind would quickly grow sufficiently adult to make good use of the unbelievable powers it had acquired over nature.
He handed us the power to destroy ourselves or the power to build an entirely new future. The choice was left to us.
And connecting that profound hope to his famous paradox, the absolute silence of the stars, leaves me with a deeply chilling thought to end on. What if the reason we haven't heard from anyone else out there in the dark universe is because other civilizations reached their own 1938? They discovered their own atomic fire, and they simply failed Fermi's test of adulthood. A single mistake, just like misinterpreting a shattered uranium atom, and the chain reaction of their own destruction couldn't be stopped. Something to mull over the next time you look up at the night sky.